page A16, Appendix C, we're looking at graphs of second-degree equations. And when we think of second-degree equations, we primarily think of circles, parabolas, ellipses, hyperbolas is what we're focusing on in this appendix. So let's start with circles. Remember that the standard form of a circle is x minus h squared plus y minus k squared is equal to r squared, where our center is hk and our radius is r. So if they gave me, for instance, example 1, they gave me a circle with center 2, -5 and radius 3, and they asked me to create the equation in standard form, what am I going to have down here? X minus 2, y plus 5. And then over here for my, on the other side of my equal sign for my radius squared? 9. So that would be the standard form of my equation. All right. Then they asked me to go the opposite way. They give me the equation, and they ask me to come up with the center and the radius. And of course, they're not going to give it to me in standard form. So how do I get this in standard form? Completing the square. Yes. Our favorite thing in the whole wide world. Alright, so to complete the square, let's get all of our x terms together and leave some room to complete the square. Get all of our y terms together, leave some room to complete the square, and then move that constant over to the other side. So I'm going to subtract the 7 over to the other side. When you complete the square, you take the coefficient of the middle term, cut it in half, square it, and add it to both sides. So we're going to take the coefficient of the middle term for this first set here. Coefficient of the middle term is 2. Cut it in half. That would be 1. And then square it, 1, and add that to both sides. What we do to one side, we have to do to the other. Alright, so for your second set here, if you take the coefficient of the middle term, you cut it in half, and you square it, what are you going to be adding to both sides? 9. Good. Because the -6 cut in half is -3, squared is +9, and that's what we'll add to both sides. Alright, it's called completing the square because we just created 2 perfect squares. So now we want to factor those squares down. So if we had x squared plus 2x plus 1, and we factor that down, what would it factor to be? X plus 1 squared. How about the y term? What's it going to factor to be? Y minus 3 squared. Good. And then we'll just combine our constants on the other side. So now it's in standard form. Now we can look at it and see our center and our radius. So what's your center? -1, +3. So when you've got your equation, which is x minus h and y minus k, you can kind of think of it as the opposite of those numbers. So you can think of it as the opposite of +1 is -1, and the opposite of -3 is +3. All right, then for your radius, how are you going to find your radius? Take the square root, and it's really easy to get that confused and think we're supposed to square it instead. So for your quiz over this, you can count on a problem like this, when I ask you for the radius, you can count on square root of 3 sitting there as an option and 9 sitting there as an option, so that I can tell whether you knew to take the square root of it or to square it. So be careful with that, because over here we have to square it, whereas over here we have to square root. So look at your equation carefully and think about what you're trying to do. All right, then we want to look at parabolas over on page A18. Basically, there were 4 different shapes to our parabolas that we looked at last year. There's the standard shape that we're used to when we have y is equal to x squared. So if you have y is equal to x squared, that's a parabola that opens up. Now, of course, there's all kinds of things that we can do to that. We can have values subtracted from x and values subtracted from y that are going to cause horizontal and vertical shifts. We can have negatives that cause reflections. All types of things. And so remember that when your leading coefficient is positive, it opens up. But when your leading coefficient is negative, that's like you threw a negative out in front of the whole function. That causes it to reflect in the x-axis, right? And so that causes it to open down. So that was the second shape that we had. that was if you have a negative out in front of the whole thing, it's going to reflect in the x-axis and it's going to open down. If you look at the third shape over here, we've got x is equal to y squared. If you compare our first form, y equals x squared, with our third form, x equals y squared, what's happened? They switch places, right? X and y switch places. When do we switch x and y? What do we use that with? Yes, with an inverse, yes. So you switch x and y when you're working with inverses. If you know the graph of the original, how do you graph the inverse? It reflects in some line. What's that line? Y equals x. Nice, yes. So if I drew for myself kind of an imaginary line here at y equals x, and I reflected that parabola across that line, then this is the image that I would get. And that's why when I graph x equals y squared, that's why it's a parabola that's opening to the right. It's just the inverse of that one that opens up. Again, when you put a negative out in front, we run into reflection. So when we put a negative out in front, then it's going to cause a reflection in my y-axis. Now, an easy way to remember this is they always open in the direction of their leading coefficient. What I mean by that is this leading coefficient was positive, so it opened in a positive direction. This leading coefficient was negative, it opened in a negative direction. This leading coefficient was positive, opened in a positive direction. This leading coefficient was negative, opened in a negative direction. So it's always pointing towards the positive or the negative numbers for the axis that it's on based on that leading coefficient. Okay? Now, those are just the base graphs, but of course, again, we could have values subtracted from x and y that would change our vertex. We could, so that it would be shifted. We've dealt with reflections and that type of thing before as well. If you're working with a parabola that's in standard form is not what we think. We tend to think of the standard form of a parabola to be this. It is not. It's that ax minus h squared plus k form that you can just look at and automatically see hk, see your vertex, then that's your standard form. If they don't give it to you in standard form, let's say that they do give it to you in the ax squared plus bx plus c form and you want to graph it, if you have your vertex and the direction it opens, that really is the best way to start graphing your parabola. So just a reminder that an easy way to find the vertex when you're in that form is that you could do negative b over 2a to get the x value of your vertex. And then, of course, once you know x, you just plug in to find y. All right, so example number 4 really leads us into our purpose for conic sections in calculus. Example number 4 says, sketch the region bounded by the parabola x equals y squared, bless you, and the line y equals x minus 2. All right, so if I've got x equals y squared, which way does that open? Yeah, so it's centered at 0, 0 and opening to the right. So there's that parabola that we were working with previously. And then they want us to graph y equals x minus 2. So however you prefer to graph a line, since it's in slope-intercept form, I probably would say I have a y-intercept at negative 2 and a slope of 1. So I'd come down here to my y-intercept of negative 2 and I'd rise 1, run 1, rise 1, run 1. Or you could find your x and y-intercepts or an xy chart, whatever you want to do. So example 4 says, sketch the region that is bounded by these two graphs. When it says bounded by, it's basically the idea of what just got fenced in, what just got enclosed, what is bounded on all sides. And so the region that just got bounded is this little highlighted region right here. So right now they're going to have us identify that region, but later on in the year we'll calculate the area of that region. We will revolve it around an axis and create a three-dimensional figure and find the volume of that figure. So that's why they want us to be able to generate regions based on our conic sections. That's where we're going with it. All right, bottom of page A19, they talk to us about an ellipse. And remember, the ellipse is the one that kind of looks like an oval. Ellipses and hyperbolas are very similar in terms of their descriptions and some of the formulas that they have. And so we want to focus on the ellipses today, and then we can see the differences with the hyperbolas in the next half of this lesson. So to begin with, the equation that they give us on A19 for an ellipse is that it's x squared over a squared plus y squared over b squared is equal to 1. But I would warn you that that equation can be drastically altered. Like a is not always grouped with x. A is related to the major axis, which we'll talk about in a second. So A is always going to be grouped with the major axis. So if Y were the major axis, then A would be over here with Y. So these can definitely switch places. A can be grouped with X or Y. Additionally, to start with, they're just giving us ones that have no value subtracted from X or Y. So they're not being shifted at all, so that means their center's at 0, 0. But we will see ones later on in this section where we do have values subtracted from x and y, and that alters the look of the equation as well. So I just wanted to give you a warning that it's not always going to look like this. However, if an ellipse equation is in standard form, it's always set equal to 1. The major axis in an ellipse is the larger one. So you can have the oval where the major axis is horizontal to look like this, or where the major axis is vertical to look like this. The major axis is going to be the larger one. The minor axis is going to be the smaller one. A will be defined as the distance from the center to the endpoints of the major axis that are called the vertices. B is the distance from the center to the endpoint of the minor axis. All right? So example 5, they give me this equation and they ask me to sketch its graph. Well, looking at that, I don't even know what that is. I mean, that just doesn't look like... Okay, well, if it's x squared and it's y squared, then it can't be a parabola, right? It's either got to be a circle, ellipse, or hyperbola. Now, although we've not looked at this yet, we know that x squared minus y squared is the hyperbola. So that means we're down to a circle and an ellipse. In a circle, your a and your c values, the number in front of x squared and the number in front of y squared, would have to be the same. So this can't be a circle. This has got to be an ellipse. Okay, well, it doesn't look like an ellipse. Well, that's why we said that when an ellipse is in standard form, it's set equal to 1. So we need to get this thing set equal to 1, and then it'll start shaping up and looking like it's supposed to. So let's go through and divide everything by 144. All right, so now it's starting to look a lot more like an ellipse. What is my center going to be? 0, 0. Nothing being subtracted from x, nothing being subtracted from y. So my center is 0, 0. What's my major axis, x or y? X. How do you know? 16 is bigger than 9. Good. All right, so what's my a value? 4. What's my b value? 3. So I'm going to come over to my graph and say, okay, if the major axis is horizontal, then the distance from that center of 0, 0 to the endpoint of the horizontal major axis is 4. So I'm just going to go 4 to the right and 4 to the left. And then b is 3, and that's the distance from the center 0, 0 to the endpoint of my minor axis, which is vertical. So I'll go up 3 and down 3. And then I can sketch my graph. All right, so that's where we're going to stop for today. And that's where the material for your quiz is going to stop as well. So for your homework tonight on page A23, we're doing 1 through 13 odd, omit 9 out of that 1 through 13 odd. Then you're doing in addition number 33, challenge number 19. So we've got our first quiz tomorrow. No calculator for that quiz. And you need to be sure that you review over your quiz policies. If you had any questions about those, then feel free to ask me about those.